Hi Physics 131. So we're going to continue with Chapter 2. We're in Section 2.5 on paper page 58 and the PDF page 76. This section is called Motion Equations for Constant Acceleration in One Dimension. We should start with notation T, X, V, and A. So first, let us make some simplifications in notation. Delta T is T final minus T initial, but T initial, we can usually set that to be 0. That's sort of the definition of initial time, is when T equals 0. So delta T equals T final, and we're just going to call that T, the time. Delta X is X final minus X initial. Delta V, change in velocity, is V minus the initial V. So 0 denotes an initial value, and the absence of subscript denotes the final value in whatever motion is under consideration. And at the top of the next page, we have this notation A for acceleration. So the assumption of this section is that acceleration is constant. And I just want to remind you that there are lots of examples of motion which acceleration is not constant. When you think about the moving man FET animation from last class, you could see that there was a graph of acceleration versus time, and it went all over the place. And there's a lot of examples of that. So when is acceleration constant? Well, one good example is falling. Or what we call a free fall. If something has only one force on it, and that's the force of gravity, then it's going to have a constant acceleration downwards of 9.8 meters per second squared. And there are other examples where acceleration can be constant. So if that is the case, then the average acceleration is equal to the instantaneous acceleration because they're constant. And in that case, we can derive these equations of constant acceleration. So I think we're going to go to the whiteboard to actually derive these equations rather than go through the textbook. So I'm going to call this the equations of constant acceleration. And by definition, the average velocity, which is v with a little line on top, meaning the average, is equal to the change in position divided by the change in time. And with that notation we talked about before, that's going to be x minus x initial divided by the time. And what we can do is rearrange that, multiply the left and right hand sides by t, and you get v average times t is equal to x minus x0. And then you can add x0 to both sides, flip it, the x to the other side, and you get x equals x0 plus v with a bar on top times t. And your book calls that one equation 2.50. And the next thing is just this sort of obvious idea, which is that the average velocity, that I guess if acceleration is constant, then the average velocity is the final velocity plus the initial velocity divided by 2. It's halfway between the initial and final. And your book calls this one equation 2.51. But what I'm going to do is combine these two equations. I'm just going to plug this into here. Combination equations 2.50 and 2.51. It's a combination equation 2.50, 2.51. Is going to be x is equal to the initial x plus v0 divided by 2 all times t. And I'll call that equation, 2.51 b or something like that. So that's a good one to know. First equation of 4. Second equation is from definition of acceleration. Well, actually, this is the definition of average acceleration, but that's the same as acceleration if A is constant, is just delta V divided by delta T. So again, with our definitions, that's V minus V initial, all divided by the time. And so you can rearrange that. You get A times T is equal to V minus V0. So V is equal to V0 plus AT. So I'm going to call that equation 2.52. And the next thing I'm going to do, which is going to look a little weird, is I'm going to take this equation. I'm going to add V0 to both sides. So V plus V0 is equal to 2V0 plus A times T. And then I'm going to divide both sides by 2. V plus V0 over 2 is equal to, this divided by 2 is just back to V0 plus 1/2 times A times T. Remember, this is just average velocity. So this is average velocity is equal to v0 plus 1/2 at. And if you go back to equation 2.50, remember that x is equal to x0 plus the average velocity times t. So I can take this and just plug it in to right there. And I get that x is equal to x0 plus, and all this stuff. So v0 plus 1/2 a times t, all times t. Now I can take that t and multiply it in, and I get x is equal to x0 plus v0 times t plus 1/2 a t squared. And this is called equation 2.53. So the last thing is that if we take equation 2.52, which remember was v is equal to v0 plus at, and we solve this for t, we get that v minus v0 is equal to a times t, divide both sides by a, and we get that t is equal to v minus v0 divided by a. And of course we also have that v average is equal to v plus v0 all divided by 2. Again, let's go back to equation 2.50, which is that x is equal to x0 plus the average speed times the time. So what I'm going to do is a little kind of complicated, but I'm going to take this average v, I'm going to plug it into there, and then take this t, and I'm going to plug it into there. And so I can write out x is equal to x0 plus v plus v0 all divided by 2 times v minus v0 all divided by a. And so, I don't know if you remember your algebra, x is equal to x0 plus 2a is on the bottom, and we've got v plus v0 times v minus v0. So when you take a plus b multiplied by a minus b, you end up with a squared minus b squared. So x is equal to x0 plus v squared minus v0 squared all over 2a. Actually solve this for the final velocity squared. So first thing I'll do is I'll subtract x0 from both sides, and I've got v squared minus v0 squared all over 2a. Now I'm going to multiply both sides by 2a, so I'll get 2a times x minus x0 is equal to v squared minus v initial squared, and then I'll add v initial squared to both sides, flip it around, and I get v squared is equal to v initial squared plus 2 times a times x minus x initial. And this one is the last of our 4 equations, and this is called equation 2.54. And here they are. So the textbook lists these as 5 equations, but I have combined the first 2 with the v average to be just one equation, x equals x sub 0 plus this average speed times t. So if the acceleration is constant, then you can find x this way, and then there's the other 3 equations here. So I would like you to go through this chapter, try the examples, this section. You know, it's always good to read the book, but now you've seen those equations derived. And the last section for today is this problem-solving basics. And it's talking about problem-solving steps. There's no simple step-by-step method that works for every problem. The following general procedures facilitate problem solving. I think this is really, really useful. So I've taken these 6 steps and put them in a presentation. So here's College Physics' problem-solving basics for one-dimensional kinematics. It's 6 steps, which we'll start with. Step number 1 is draw a diagram. Draw a diagram, draw a diagram. I'm sorry to repeat myself, but it'll help you remember. Step number 1 is draw a diagram. Draw a diagram, draw a diagram.
Wow, that does work.
Drawing a simple sketch or diagram will help you think about which physics principles are involved. Once you've identified the physics principles, it's much easier to find and apply the equations to represent the laws and quantities. Don't forget to define your axis. or axes if it's two-dimensional. You should decide which direction is positive and note that on your diagram. And making decisions like this and sticking to them is part of how you solve problems. And if you get into trouble, you can always go back and start again and try a different decision. Step 2, make a list of knowns. Make a list of numbers that were given in the problem as stated. And you can add this right next to your sketch. For example, if it says somewhere that the initial velocity is 5 meters per second to the right, and on your diagram you identified pluses to the right, then you could write down v sub 0 equals plus 5 meters per second. And you can choose the notation. So you could, if you wanted, you could put VI instead of V0, and don't forget the units. Some numbers are inferred rather than explicitly stated. So it might say that something is stopped, or it might release from rest is another good one. It means that the initial velocity is 0. And sometimes we can define initial time as 0 or initial position as 0. So you can write those down as your knowns. Also make a list of what's called unknowns or unknowns. So in particular, what exactly needs to be determined in the problem to get the answer and to move on. Some unknowns you don't actually care about, so there's no real need to list them unless they're somehow important in determining the answer. So keep your eye on the goal here. And you might notice that you're going to use a lot of paper. I actually have a whole recycling bin, and I'll go in and use the blank sides of old paper. I find, for me, physics problem solving requires writing a lot. Step 4. Find the equation or equations that can help you solve the problem. So your list of knowns and unknowns can help. It's easiest if you can find equations that only have one unknown. If you have two unknowns, you're going to use two independent equations and combine them. You could solve for both. 3 unknowns requires 3 equations, etc. This is the tricky part, this step 4, okay? It takes some practice, and it's good to remind yourself of the physics principles during this part. The equations all mean something, and you are using them for a reason. Sometimes thinking about the reasons behind the equations helps you figure out which ones to use. There may be multiple steps if the problem is involved. Sometimes you have to first solve for one thing and then use that answer to solve for something else. So, and I'd recommend if you do this, keep things in symbolic form at this point. Don't plug in the numbers until the last second. So, and sometimes you find that one of your unknowns will cancel out and you don't have to worry about it, and that saves time. But basically, don't give up. You can do it. keep on going. To step 5. So step 5 is substitute the knowns into the appropriate equation or equations and solve for the numerical answer. This is sort of the last step. It's one of the easier parts. As long as you're careful of typing numbers into your calculator, it's not real tricky. Just do it. Don't forget, you do need a calculator for the term tests and the final exam. So I would get one now. Use it for your problem sets. Don't use your phone or Excel or something for problem sets, because you sure won't be allowed to have your phone during the tests and the exam. Also, on these steps 4 and 5, don't forget units. Your final answer will require units, and all of your knowns have units as well. So it can be a good idea to write down the units at every step. The units actually cancel just like, or multiply times each other just like other things. Just like variables. So this can be a good way to check your answer, which leads us to step 6, the sanity check. Does your answer make sense? For example, if you've been asked to calculate a distance it takes a plane to stop on the runway, and you get your answer is 0.0053 millimeters, okay, that clearly is something wrong. So take a look at your answer, think about what's going on and what the physics is, and decide if it seems okay. And if it doesn't, you can look back for mistakes in the first 5 steps. And here's the last step is just do a units check. Look at the units. If you've been careful about keeping track of your units in the previous couple of steps, then they should match up here. You should get, meters per second if it's velocity, or meters if it's distance, etc. And that is it for your reading for today. I'll see you next time when we finish up chapter 2.